Another theorem says that every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. When we're talking about irreducible quadratic factors, we're talking about things like x squared plus 9 or x squared plus x plus 1. These are quadratic expressions that you cannot factor over the real numbers. If we had to factor x squared plus 9 in the complex number system, that's x plus 3i and x minus 3i. And so that is an irreducible quadratic because it does not factor over the real numbers. You have to have non-real complex numbers in there in order to factor it. And so this theorem is basically saying when you have a polynomial with real coefficients, you're either going to have linear factors like x minus 5, or you're going to have irreducible quadratics like x squared plus 9 or x squared plus x plus 1. And so now, with all that in hand, we're ready to go through the process of finding the complex zeros of a polynomial function. Now, to do this, we're going to follow the exact same steps that we followed when we were looking for the real zeros of a polynomial function. Let's look at an example. We're going to find the complex zeros of the polynomial function f of x equals 2x to the fourth minus 11x cubed plus 13x squared minus 44x plus 20. And we're going to write f in factored form. So the first step that you need to follow is determine the degree of the polynomial and therefore how many complex zeros are you looking for. So for example, this is a polynomial of degree 4. So f has 4 complex zeros. The degree of the polynomial always tells you the number of complex zeros. The next thing we want to do is implement Descartes' law of signs. Remember, Descartes' law of signs, or rule of signs, tells you how many positive and how many negative real zeros you may have in the polynomial function. So to determine the number of positive real zeros, what you do is look for the number of changes in sign of f of x. So I'm going to write down f of x like that. And then I look for the sign changes in the polynomial when it's written in standard form, that is descending order of degree. So like here, I go from a positive coefficient 2 to a negative coefficient 11, negative 11. And so that's a sign change. Now I go from negative 11 to positive 13, another sign change. I go from positive 13 to negative 44, another sign change. And I go from negative 44 to positive 20. That's another sign change. And so there are 4 sign changes in f of x. Therefore, there are 4, 2, or 0 positive real zeros for this function. And then we want to find or determine the potential number of negative real zeros. To do that, you evaluate f of negative x. So that's 2 times negative x to the fourth minus 11 times negative x to the third plus 13 times negative x squared minus 44 times negative x, and then plus 20. So this is 2x to the fourth plus 11x cubed plus 13x squared plus 44x plus 20. Notice that all of my coefficients are positive, and so there's no sign changes at all. Therefore, there are no negative real zeros. I don't have to worry about negative real zeros at all for this function. The third step is to list the potential rational zeros. So to find the potential rational zeros, remember you list out all the factors of the constant and all the factors of the leading coefficient. The factors of the constant are referred to as P. Here's my constant, it's a plus 20. And so the factors are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Because remember, what we're doing here is just basically looking for factors of 20. And so 1 and 20 works, and then you put the plus or minus. 2 and 10 work, and 4 and 5 work. And you remember, you put the plus or minus because it could be like positive 4 times positive 5 gives me 20, but negative 4 times negative 5 also gives me 20. And then for Q, it's the factors of the leading coefficient, which is 2. So that's just plus or minus 1 and plus or minus 2. And now we form all possible ratios of P over Q. So the way I do this is always 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, 20 over 1. And then I go through my P again with the second factor for Q. Well, 1 over 2, 2 over 2, etc. So again, 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, 20 over 1. Then 1 over 2, 2 over 2, but that's 1, 4 over 2, but that's 2, 5 over 2, 10 over 2, but that's 5, and 20 over 2, but that's 10. So I've exhausted my list of potential rational zeros. Remember what this list means. If you're going to have a rational zero, it must come from this list. So we know, for example, 3 is not a rational zero of the polynomial function f because it's not in this list. 2 might be a rational zero, but it might not. So your options here for narrowing down this list, option 1 is just to go through the list and see which ones give you 0 as an output. But the second option is to go back and graph this polynomial function and see if where the graph appears to be crossing the x-axis. So we're going to use that route. So go back to your graphing tool. Like you could use your calculator, or you could use GeoGebra, and there's your graph. We're not worried about a complete graph at all. We just want to know where the graph is crossing the x-axis. So like it looks like it's crossing the x-axis at 5 for sure, and it's crossing the x-axis maybe at -1/2. To see if 5 is a 0, just evaluate the function at 5, and you get 0 out. See that? So because f of 5 equals 0, we know x minus 5 is a factor of f. So you're going to divide x minus 5 into f. And the easiest way to divide by x minus 5 is to use synthetic division. So you put the 5 on the outside, and then we put our coefficients of x in. So on 2, negative 11, 13, and then negative 44 and 20. That's the constant, that's the coefficient on x squared, x cubed, and x to the 4th. So with the synthetic division, you bring down the leading coefficient. And then remember what we do here is we say 5 times 2 gives me 10. Add vertically, negative 11 plus 10 is negative 1. And repeat the process. 5 times negative 1 gives me negative 5. Add vertically. 13 plus negative 5 gives me 8. 5 times 8 gives me 40. Negative 44 plus 40 gives me negative 4. 5 times negative 4 is negative 20. 20 plus negative 20 gives me 0. And remember what these values represent. That is your remainder. We knew our remainder was going to be 0 because f of 5 equals 0. Negative 4 is your constant. 8 is your coefficient on x. Negative 1 is your coefficient on x squared. And 2 is your coefficient on x cubed. So now you can say f of x equals x minus 5 times 2x cubed minus x squared plus 8x minus 4. And we've partially factored the polynomial. And again, we know 5 is 0. And now that we've done that, our goal is to work on the expression 2x cubed minus x squared plus 8x minus 4. If we go back to our original graph, it looks like 1/2 is a 0, and it is. Because f of 1/2 equals 0, I know substituting 1/2 into the expression underlined in green is going to give me 0. Because putting 1/2 in for x minus 5 does not give me 0. The only way the overall expression can be 0 when I evaluate it 1/2 is if this expression is 0. And so now I'm going to say that because f of 1/2 equals 0, x minus 1/2 is a factor of 2x cubed minus x squared plus 8x minus 4. And so I'm going to divide by x minus 1/2. So that's 2, negative 1, 8, and negative 4. So I bring down my 2, and now I do the multiplication. 1/2 times 2 gives me 1. Negative 1 plus 1 gives me 0. 1/2 times 0 is 0. 8 plus 0 is 8. 1/2 times 8 is 4. Negative 4 plus 4 is 0. And so there's my remainder as I would have expected. So now f of x equals x minus 5 times x minus 1/2. And then I'm left with 2x squared plus 0x plus 8. I can factor out a 2 from this expression, and I'm left with x minus 5 x minus a half, and then x squared plus 4. Now my goal is to find the complex zeros of x squared plus 4. I can do that on the side. Just solve x squared plus 4 equals 0. Now for this one, I can subtract 4 from both sides and then take the square root of both sides like so. The square root of negative 4 is 2i. And so I'm left with x equals plus or minus 2i. If I couldn't do this, I could always use the quadratic formula on any irreducible quadratic to find the complex zeros. And so now I have 2 times x minus 5 times x minus a half times x minus 2i times x plus 2i. It's completely factored. I have 4 linear factors because it's a polynomial of degree 4. It turns out here each of the 4 zeros are distinct. I don't have any repeating zeros whatsoever in the polynomial. And so really the process is identical to what it was earlier when we found the real zeros. The only new piece to the puzzle is finding the non-real complex zeros when you have an irreducible quadratic expression. Other than that, completely the same.